Now we're going to look at how to take parametrically defined functions and to rewrite them in rectangular form, or Cartesian form. Means the same thing. We want to take instead of having two equations dependent upon the parameter t, we want to make y depend on x or x depend on y. Now the strategy is this. If possible, I would like to rewrite one of the easier looking equations to be t equals and substitute into the other one. And we're going to see that right here in the very first one that I'm going to do. So I'm going to take my equation, one of them, and it doesn't really matter, and I'm going to pick to write it as t equals. So I'm just going to pick the x one here and say, all right, I want to write that thing as t equals. So I'd add the 1 to the other side, so it'd make x plus 1 equals 3t. And then I divide by 3, and so t is equal to x plus 1 over 3. So I have that. And now I'm going to take this, and I'm going to take that, and I'm going to substitute it into my y equation where t is, and I'm going to rewrite. So my y equation becomes y equals 2 times, and then I put t in. So x plus 1 over 3. And then I finish writing the rest of y. And then we would clean that up a little bit, so that'd make y equals 2/3 x plus 2/3 plus 1. And we get y equals 2 over 3 plus, or x, sorry, plus 5/3. And so there's my rectangular equation for those parametrically defined functions. Now, if I start to see trig, it gets a little bit more complicated, all right, because we want to try to avoid using inverse trig functions if possible, especially if I have two different functions, all right, because if I apply inverse sine to a cosine or vice versa, it's just going to make a pretty complicated mess. So what we're actually going to do is we're going to look to use a trigonometric identity. And the trig identity that we're going to look to use is a Pythagorean identity that says if you have sine squared, I'm going to change it to, if I have sine squared t plus cosine squared t, that's going to equal 1. So I need to take my two equations and I want to isolate the variables, all right, or isolate the trig function, sorry. So for my x equation, that's x equals 4 sine of t plus 2. I'm going to subtract the 2 to the other side and divide by 4. So I have x minus 2 over 4 equals sine of t, and I can leave it in that form. And then I'm going to do the same thing for y and say isolate that trig function. So it's really y equals 2 cosine of t, forgot the s, 2 cosine of t minus 1. Add the 1 to the other side, divide by 2, and there's my cosine function isolated. Or our Pythagorean identity says that if I were to square the sine and square the cosine, add them together, they would make 1. So I'm going to take those two equations, I'm going to write them above one another. So x minus 2 over 4 equals sine of t. And then I have y plus 1 over 2 equals cosine of t. And in order to apply that identity that we want to use, this sine squared plus cosine squared equals 1, I have to square the sine and the cosine and add them together. Well, I can't just do that to the right-hand side. If I'm squaring an equation, I have to square both sides of it. So I'm going to square both sides and add there as well. And when I do that, what I get, sine squared plus cosine squared makes 1. And we have x minus 2 squared. I didn't leave myself enough room because I have to add those. So I'm going to have x minus 2 squared over 16 plus y plus 1 squared over 4. And I can leave it like that. That's actually the standard form for an ellipse. All right, let's look at another one. So similar scenario here, but instead of seeing sine and cosine, I see cotangent and cosecant. And the Pythagorean identity that deals with cotangent and cosecant is 1 plus cotangent squared, and I'm going to just say theta, equals cosecant squared of theta. And so I want to isolate the trig functions just like what we did in the previous one. And so I'm going to isolate the trig function for the x equation. And if I do that, that's going to make I'd have x plus 1 divided by 4 equals cotangent of 2t. And then I'll do the same thing for the y equation. So I want to isolate the trig function there. So that'd make y minus 2 divided by 2 equals cosecant of 2t. And I'm looking at the Pythagorean identity. It has to deal with cosecant, cotangent, and I want to make that equal 1. So actually what we would do is we would isolate the 1, subtract the cotangent squared to the other side, and I have cosecant squared of an angle minus cotangent squared of an angle is equal to 1. Well, it doesn't matter that I have two t's inside a cotangent and cosecant, because technically those are the thetas. So as long as I square those two functions and subtract them in the correct order, I can make them cancel out in this system to make it equal 1. So I'm going to perform that kind of subtraction, where I need to make sure I subtract. I have cosecant squared minus cotangent squared. So I'll go y minus 2 divided by 2 is equal to cosecant of 2t. And then we'll write up under it our cotangent equation. X plus 1 over 4 is equal to cotangent of 2t. And in order to use that identity, I have to square the cotangent and the cosecant, and I have to subtract them. Cosecant squared minus cotangent squared. That's going to give me 1. So I have 1 equals. Now, I also have to square the left-hand side of those two equations and also subtract them. And so I'll start, and that's going to make y minus 2 squared over 4 minus x plus 1 squared over 16. And that we're going to leave it like that because it's actually the standard equation for a hyperbola. One more example. All right, this time I don't see any trig. So I'm looking to see if there's an easier approach to doing this problem instead of taking the x equation and rewriting it as t equals, which I absolutely could do. And I'd still get the right answer, but I'd have to be careful. If I'm looking at this y equation, and this is an algebra trick that is sometimes useful, is I want to see if I can't rewrite the y equation to show what I'm doing to 2t everywhere. So y could equal, now I think about how do I make e to the 2t power? Well, our properties of exponent says if you have a power raised to a power, you multiply their exponent. So if I have e to the 2t squared, like this, that would create e to the 2t. And then I have plus 2 times e to the t minus 1. Well, e to the t is really x. So everywhere I see e to the t, I can replace that with x. And we've actually eliminated the parameter without writing this equation, or either of the equations, as t equals. And you get x squared plus 2x minus 1.